Hello, today I would like to share my previous research named Robust Dynamic Bus Control, a Distributional Multi-Engine Reinforcement Learning Approach. This report consists of three parts. The first is the background. I would like to introduce the problem we study and its motivation. Like most physical systems, the transit system is not a stable system in nature, and the instability comes from the uncertain demand, traffic congestion, and other interruptions. Such uncertainty will result in one of the common phenomena during transit operation called bus bunching. As you can see from this small video and the figure, bus bunching means two or more buses arrive at the same bus stop nearly simultaneously. When bus bunching happens, there may be multiple buses at a stop with fewer waiting passengers while a longer queue exists at another bus stop. Besides, we will see some buses are vacant while others are full of people. Thus, some passengers have to endure a long waiting time and some have to experience back in vehicle service. Hereafter, the transit system's efficiency and attraction will undoubtedly be decreased. As a result, to provide reliable and efficient transit service, we need real-time control strategies to avoid bus bunching and maintain the regularity of the bus service. Recent research has demonstrated the promising application of multi-engine reinforcement learning to achieve efficient bus holding control to avoid bus bunching, but previous studies overlooked the robustness problem resulting from the randomness in the bus system. Specifically, they do not explicitly consider perturbations and anomalies in transit demand or traffic state, which is of most importance when transferring multi-engine reinforcement learning to real-world application. So the optimal goal of this study is to fill this gap by developing a robust multi-engine reinforcement learning framework for transit control. The issue of robustness is related to the uncertainty or randomness of the system. To achieve robustness efficiently, we introduce distributional reinforcement learning to account for the randomness. Specifically, when using reinforcement learning to achieve control for the bus system, the system's randomness is essentially modeled in state transitions, rewards for the action, and then the long-term return as shown in this equation. With distributional reinforcement learning, we can learn a state action value distribution to evaluate and then update the control policy. In this way, we can capture the randomness in the intrinsic uncertainty of Markov decision process for the bus system. In addition, distributional reinforcement learning can facilitate risk-sensitive policy learning, which turns out to be helpful in our later method modeling. To take advantage of distributional reinforcement learning in the multi-engine setting of our problem, there will be two challenges to fix. The first is how to handle the uncertainty with distributional reinforcement learning in multi-engine setting, and the second is how to address the credit assignment problem with distributional reinforcement learning in multi-engine setting. Before introducing our method, let's first review some basic preliminary. In reinforcement learning, an engine interacts with the environment by recursively taking action and observing a new state, then collecting the reward. Reinforcement learning allows engines to learn from this kind of interaction to gain maximum cumulative reward, as shown in this equation. And there are mainly two categories of reinforcement learning methods. For the value-based methods such as Q-learning and DQN, they use the state action value function for policy evaluation. The basic idea is that after achieving a reasonable estimate of the optimal state action value function, the optimal policy will be the one choosing the action with the highest return at each state. And the policy gradient is directly optimized the return by using gradient action method. Unlike traditional reinforcement, which learns the expectation of cumulative reward or the state action value, distributional reinforcement explores learning a state action value distribution. To facilitate such learning within a traditional deep reinforcement framework, the state-of-the-art solution is to approximate the target distribution with quantile function. And this is the formulation of the quantile function. Actually, the quantile function of a probability distribution is the inverse of its cumulative distribution function. So we can actually approximate a distribution using the quantile function. And in distributional reinforcement, it actually approximates the action value distribution with quantile function. And we can trade the quantile function with quantile regression by minimizing the weighted pair Haber regression loss of different quantile fractions. With a learned quantile function, we can take a further step as stated by previous study. Any distorted expectation can be represented as a weighted average over the quantiles. In this study, we would like to exploit this idea by distorting the action value expectation. In this way, as shown in this figure, the distorted rate essentially indicates the attitude towards the quantiles of the action value distribution. For example, the risk-averse place lower weight on larger quantiles. Therefore, we can trade the policy with different risk preference using the distort state action value expectation. And the last technique we utilize in this study is meta-reinforcement. And this technique is proposed in the previous NIPS paper called meta-gradient reinforcement. The basic idea is to introduce meta-learning scheme to improve learning performance of reinforcement learning. In particular, it optimizes the hyperparameters in reinforcement learning, which will turn the differentiable ingredients in the reinforcement pipeline using higher order gradient. Intuitively, after every update on the theta is the parameters of the engines. The meta reinforcement will adapt the meta parameters to a direction that achieve the better performance. And here the theta is the parameters for the engine. You can regard it as the parameters of the policy, and then the eta is the meta parameter, which can be trained using higher order gradient to further improve the performance of the engine. Okay, and then we will introduce the proposed multi-engine reinforcement intrinsic control framework on top of the distributional reinforcement, distorted state action value expectation, and meta reinforcement. First of all, we would like to look and formulate a bus control framework in view of multi-engine reinforcement setting. We treat each bus in the transit system as an engine. It will determine the holding duration on each arrival based on a predefined observation, and then receives its feedback for the previous control at the next arrival. The previous studies generally introduce traditional actor-critic framework to learn the bus control, in which the policy evaluation is directly approximated by a critic given a local observation. To account for the uncertainty in the transit operation, we propose to use distributional critique and then learn the quantile function for the state action value for the policy. In a multi-engine system, the contribution of each actor or the engine or the system is uncertain due to the intrinsic randomness of the system and the action of other engines. To account for this issue, we distort the evaluation of policy from the critic. Intuitively, you can regard the distorted rate as confidence or the preference. And to be more specific, the distortion rate is the confidence in the actor's contribution based on the idea of the risk-sensitive policy reinforcement. In this study, the risk-seeking means that we have high confidence on actors' contribution, which means that the return of the evaluation for this actor is largely related to its own action at its last arrival. It actually means that the performance of the current system has a large relation to his holding control at his last arrival of a bus stop. And the risk averse means that we only have low confidence on actors' contribution, which means that the current state or the performance of the system is less related to the policy of the actor to the policy of the evaluated actor. And the neutral means that we do not show any attitude on the actor's contribution. And at this point, we already built the basic architecture of multi-engine reinforcement learning framework using distributional reinforcement learning and the idea of distorted expectation. The next step is to introduce meta-learning to further facilitate the distributional reinforcement learning. The meta-learner is introduced to learn the distorted rates for the control framework. And in this study, the meta-learner takes the similar structure and information we proposed in the previous study, which is proposed in IJCAL 2021. The distortion rates are dynamically determined based on the asynchronous events between two consecutive actions of an eager engine. And in this way, we actually use the actor learner to learn a good distorted ways to help the distributional reinforcement learning in the multi-engine setting. And we will validate the performance of this technique in the experiments. And then we will introduce our experimental study. And first, let me introduce the setting of this study. And we actually build a simulation test bed for these experiments. And we set the alighting and boarding times per passenger as 1.8 and 3. And the speed of buses between every two consecutive stops is random. And we also restrict the capacity of the bus as 120. Then we use 4 real-world bus lines to set up the simulation, and here are the information of this bus service. And we also validate the simulation by comparison between simulated journey time and actual journey time for the one of the bus route. And we can see that the simulated results and the actual result is very similar. Then during training, we introduce 2 uncertainty to allow the engines to learn in rich informative environment. And for the demand uncertainty, the distributed transit demand from origin I to destination J is formulated as this formula. And the traffic state uncertainty, we disturb the transit. This is the traffic state, which means that the traffic state from stop I and stop J, it actually controls the randomness of the speed of the bus starting from stop I and stop J. Actually, this is the two uncertainty we consider in our study. And then we compare our proposed methods with the following baselines. The first is the no control, which means that the bus is free to serve passengers without any intervention. And the forward heavy base control is a baseline as a traditional control scheme. And we also use independent active critique to act as a baseline as reinforcement without consideration on other engines. And we use this framework, which is based on our private study as a state-of-the-art baseline for the multi-engine reinforcement in bus holding control. And to implement ablation study, we introduce three addition experiments. The first is the distributional reinforcement with risk seeking, which means that we always place higher confidence on the engine's policy. And in other words, we actually distorted the function with we distorted the action value expectation with this distortion function. In this way, we can show high confidence on the engine's contributions to the system. And we also use distributional reinforcement with risk-averse distortion function to represent the lower confidence on the actor's contribution to the system. And finally, the distributional reinforcement with neo distortion function is introduced to act as a baseline for the distributional multi-engine reinforcement. Then we use the phi matrix to evaluate the performance of the control policy. And here are the results. The first is the evaluation on the traffic state perturbation. And this IQNCM means that it is our proposed framework which use the distribution reinforcement and the meta learning. And it achieves the best regularity on the system with a moderate increase in travel time. And we can also see that the other distributional reinforcement methods are less effective. Interestingly, models considering global information, the proposed framework, and the CAAC, the private proposed framework, perform better, especially when more uncertainty is introduced, which means that the global information is beneficial to implement an efficient transit control. And also we can see that the distributional reinforcement with confidence setting will encourage less holding period as it places less confidence on the contributions of the EcoBus. Actually, this model is distributional reinforcement with risk averse, which means that we show lower confidence in the actor's contribution to the system, and as we have less confidence on the contributions of the actor, then the actor has to the actor only considers is control performance instead of the system performance. So he will only reduce the holding period. In this presentation, I did not introduce the reward function of the engine, and the reward function actually consists of two terms. The first is the term related to the performance of the system, and second term is related to the control penalty. And for the control penalty is actually the reward that only related to the engines itself. So the model with lower confidence on the on the actual actor's contribution means that the engine will only care at the control penalty to increase its reward. And similarly, we can see that in the traffic demand perturbations, we have also seen that the proposed method can achieve the better performance. And then we also evaluate the methods on some abnormal situation in addition to the randomness. The first is the traffic state anomaly, which means that there is some accident on the road which interrupts the traffic, and usually it means that the bus will travel much more slowly than normal situation. And the basic setting is that we randomly select 4 buses suffering traffic interruption, which means that the speed is scaled by 0.1 in this setting. And the other kind of anomaly is traffic demand. In this situation, we randomly select 3 stops and impose additional 50 passengers on each bus arrival for an 1-hour span. In this way, we simulate the demand surge due to some special events in the neighboring area of these stops, such as a music concert in the neighborhood of this stop. And here is the trajectory of different control strategies under this anomaly. We can say that the proposed method can achieve the stable performance, and even if there is an anomaly of traffic state or traffic demand, it can recover the bus regularity quickly and then maintain the regularity in the downstream operation. And we also analyze the interpretability of this model. The major concern is the interpretability of the method distortion rates, because we suggest that the distortion rates indicates the confidence on the actor's contribution. So we can see that we want to see how the method distortion rates vary before training and after training, and to see what it actually represents. And we can see that before training, the model placed higher confidence on the contribution of the ego bus. Look at this. Especially before training, we can see that and 1, 2, 3, 4 means that the control events of the number of control events of other engines between the 2 consecutive control events of the ego engine. The more control events means that there's a larger probability that the current actor, the contribution of the current actor will be less. How do I say? When it is 1, it means that during the 2 consecutive control of the ego bus, there is no other buses implement control decisions. In this way, in this situation, it means that the system performance or the state of the system is only related to the current ego engine. And after training, we can say that the method learning places higher confidence on the contributions of ego engines when there are fewer other control events. It makes sense, because if there are no other control events between 2 consecutive holding decisions of the ego bus, its holding should have a more dominant impact on the dynamic of the system. Therefore, the distortion rates should give high credit on its action, and the actor should have a larger confidence to evaluate and update its policy according to the current state performance. Okay, let's have a summary of this study. And to the knowledge of our study, to the knowledge of the orders, we introduced we first introduced distributional reinforcement learning to achieve robust control during transit operation in a multi-engine setting. And we design a meta-learning framework to adapt the distributional reinforcement learning for robust multi-engine training. And then we evaluate the proposed framework, compare on multiple baselines, and comprehensively analyze the result under different situations in transit operation. Thank you for listening.